It's now 2:30, and I welcome you to this session called Lithium Post Batteries, or I would rather call it Future Emerging Technologies. And I'm Kristina Edström. I'm Director of BID2022, which means that I work on a chemistry-neutral roadmap, trying to enable the batteries of the future that we will discuss now. It means also that I'm in this respect is actually language or country neutral. And so I represent 24 different countries in Europe from south to north, and that's very great. And you will hear 3 speakers today, and they have all very well established in their fields. And so you will hear about different kinds of new emerging technologies, and you will hear also about the journey from research to make an SME in one of the future emerging technologies and the road to take to that, and also perspectives on the different, from the view of electrolytes. So I hope you will find our 3 presenters interesting and that you really join in the discussion. And those of you who are online, I really hope you put your questions in the Q&A. And we will also do like this, that we give these presentations first, and then we have a discussion, and they will come up on stage here. The 2 ones we have in the room, and also Professor Patrik Johansson from Chalmers, who we have online, our expert on electrolytes. I would like, though, first to really, well, that was me, we skipped me, but I would like to show this picture, because this is really the work we did within Batteries Europe, trying to highlight what kind of future emerging technologies do we see for the future, and when in time. And we ended up in long discussions on, can we say that these chemistries would then come on the market? And we said no, because we are not any sort of oracles or any that can foresee what future brings. But we could at least say, looking at what we are doing now, we could probably at these timelines have real KPIs that we could put that are sort of more realistic for these chemistries. Because sometimes a new chemistry, like lithium oxygen, lithium air battery, which came more than 10 years ago and became sort of the salvation of everything. And then it turned out that it was really a fantastic playground for chemists and electrochemists, because nothing really worked and everything reacted with everything. But we learned so much from it. And is it so that looking back, we can pick something that we can also look for the future? I think it's these kind of things. And if I just show a little bit, because I don't think you see it, we say here that the sodium-ion batteries come very close in time. And we'll hear more about that. We have zinc batteries we also think will come. And it's fascinating that an old chemistry like a zinc air chemistry is also a future emerging technology if we can make it recyclable with that high capacity. It's promising. And you have also flow batteries here. Go back 10 years ago and flow batteries were almost dead. They're up again. and a lot of things are happening there. We don't have any discussion of flow batteries today, but you can actually find this table in the roadmap on new and emerging battery technologies from Working Group 1. So it's online. If you search for it, you will find it. And if you go to 2030, you can see that we have sodium metal solid-state batteries. Maybe we'll handle a lot of the dendrite formation problem with sodium metal. We have multivalent systems, where anion shuttle batteries, dual ion batteries. And if we go really higher up, we hope that we can have new groundbreaking technologies. What we have to do now is to remake this roadmap, because suddenly, with the war in Ukraine and everything is happening globally, we have to reshape and rethink. And there are new things that we a little bit discarded before that we maybe should be able to do. And that is to really have the batteries without critical raw materials. We discussed it here, that really can function with many, many cycles. And that can be just as important as having really high performance. So suddenly new avenues are opening also that we have to consider. And also discussions on raw materials we had point in this direction. So we are going to start to work again to remake this picture. I just wanted to give this as an introduction. And now I would like to introduce our first speaker, who really is an expert on several of the novel chemistries or future emerging chemistries we are talking about, who has run and coordinated EU projects on this, and this is Professor Silvia Bordoadro from Polito. Please take the stage. I leave the floor to you.
Thank you. I will take this microphone. Can you hear me? Yes. Thank you very much, Christina, for the nice introduction, and thank you for giving me the opportunity to show something about the emerging technologies and what will arrive after lithium-ion, so post-lithium-ion. There will be many opportunities, so we have not the magic wand that we cannot really say today what will be the true emerging technologies, but we can do some work and thinking how to tailor the activities in order to get a better future and also a more sustainable future. So my talk will really strongly focus on sustainability that has really to drive us for next generation of batteries and next generation of our scientists. So as Christina was presenting the roadmap of batteries Euros, I took some photo from the roadmap of Battery 2030, starting from there, saying that we have in the roadmap, I wanted to show, but there's no way to do that. In any case, on the left-hand side, there's the global market demand for the applications of batteries, and everybody knows that they will grow a lot in next future, many times, and we need for sure much higher capacity of storing and maybe a lot of higher energy density for storage. And how we can achieve this higher energy storage? We have two ways. We can work both on voltage and also on capacity, and this is more or less what everybody is doing in the choices they have to do in combining anode with cathodes. So commonly, cathodes are the one working at higher voltage, and so the most of people is playing to increase the voltage always higher and higher, making in somehow, let me say also, the system to be less stable, because it's also more and more difficult to find the right electrolyte that can work properly at very high voltage. But still, this is needed in order to increase the overall specific energy. And on the other side, on the cathode, is working on the capacity. So this is the reason why there's this movement of, and this need to go again to metallic lithium, whose capacity is much higher. But in the middle, you have also two different systems, such as sulfur and oxygen. Sulfur has, for sure, lower voltage, but much, much higher capacity than many other cathodes. So combining sulfur with lithium can be a good solution to strongly increase the overall energy density. Of course, oxygen can be, and it's also very interesting, as was said before, but many, many issues are still needed to make them available in next future. So we will see that it's very interesting by electrochemical point of view, a very good game for electrochemists, and maybe in the future we will have some good opportunities. We know that all of producers look at cost as first point to drive choices. So on the right-hand side, you can see the element breakdown. One of the main elements whose cost is higher in the cell is the cathode, whose cost is around 40% of the overall cost of a battery, and then it changes depending on the composition. This is just a picture I put as a simple example to say that depending on the element, we can have different costs, but still that is the most important. But really, only how much I pay that element, that material, is the cost driver, is that we have to keep in mind for our future. Or do you really need to put in the balance, as reported on the left-hand side, on one side the real cost in terms of euros paid, but on one side, we have to put performances. Of course, we want to get the best performances possible, the battery with the best performances possible. But on the other side, we really need to become carbon neutral. So for our future, we have really to balance with the lower impact as possible. And in this sense, we can play on the material, for sure, as one of the first and the main topic on which to work. And in this sense, the UChems came, everybody knows for sure, this table of the element that reports the elements depending on their abundancy in the earthquake and their impact. And so you can see that the red elements or the orange one are the one with the highest impact, and you can see or lower abundancy, so you can immediately see that cobalt is there. But some of the others, like lithium, that is not toxic, but is becoming one of the critical elements, considering the massive use we have in the years. And some other elements are really green, so it means that they are very, very abundant. Between them, you have many alkali metals, and so Reza will speak about them later, and also sulfur as a cathode. So today, I will speak about that, taking into consideration that with EMIRI, and then this table was adopted by, let me say, everyone in Europe, classifying different generation of batteries, depending on their composition. So today we are around generation 3B, so that means that we have a high voltage cathode combined with graphite and few percentage of silicon in the cell, and we are going towards solid state. So we got an excellent talk yesterday here about solid state, that they were showing us how shorter is and closer is to the future, this kind of technology. And this will be very important even for what I will say you in a while about lithium sulfur, and I will explain you why. But today I want to focus on the so-called beyond lithium ion technologies that are the one in generation 5. Generation 5 is containing, let me say, for sure post-lithium ions, so metal ions, different than lithium, and also the conversion system. Speaking about conversion system, are systems that are not going through intercalation during charge or discharge, as commonly is for lithium, everybody knows for lithium-ion system, but they are changing their structure during cycling, and this makes also some additional issues in the cell and so on. And in this group is behaving lithium oxygen and lithium sulfur. So let me show you, this is a very dense slide, but let's start from the above figure that is coming from a publication of 1 month ago. That is very nice, that is summarizing lithium-sulfur cell. Lithium-sulfur is a very simple system somehow, because it's composed by a metallic lithium, a metal lithium as an anode, and a composite of sulfur and carbon as the cathode. And in between, there will be a liquid electrolyte. If you can check on the left-hand side here, you can immediately compare the performance of a lithium-ion cell in orange with the expected one, or the actual and the expected one for lithium-sulfur, and you can see immediately that the energy density is huge. Theoretically, it can be 5 times the one of lithium-ion, and this depends, of course, on the lightness of sulfur, the double capacity, as each sulfur atom can be reduced using a double amount of electrons compared to the elements of lithium-ion. This is quite environmental friendly because sulfur is very low cost, very highly abundant, is everywhere. We have no trouble to get it. It is also a side product of oil production, so we have a lot. So it's very simple, but why is not already on the market? So if it's so simple, because we have a lot of issues still to be solved. On one side, and I will not say anything about it, we have metallic lithium, and so all the issues already discussed yesterday during solid state talk about metallic lithium are also available here. So dendrite formation, high reactivity, and so on are always there. So we need to protect metallic lithium in order to make it working and to be very safe. So all the improvement I highlighted in yellow, all the improvement that are coming from solid state sector will be useful and easily translated here. So that's good. And on the other side, we have this composite produced with sulfur and carbon. Sulfur, of course, is an insulator element, so of course we need to increase its conductivity, and this is the reason why we are mixing together with graphite on one side. But what is happening is that the reduction mechanism is much more complex than the simple one of a lithium-ion cell, in which you have a lattice where the metal element, the transition metals are stabilized in their position in lattice, and lithium-ion are inserted and they inserted. Sulfur is composed by a circle of 8 atoms, as you can see there, and during discharge, during the reduction, it opens and it starts incorporating 2 electrons per each sulfur atom, and is adding 2 lithium ion at the opposite side of the chain. And time by time, this chain is reducing in length, and at the end of the whole process, lithium sulfide is precipitated over the cathode elements. So the discharge curve is reported here. You have 2 different steps. The first step is for the long chain polysulfides and ions that are forming, and the other one for the shorter chain. These intermediates with different length of chain are anions, and for this reason they are soluble in the electrolyte. So, of course, we can have this so-called shuttle phenomenon. It means that we can lose polysulfides during discharging, and this reduces the overall capacity. So we have 2 issues. One is related to the electrolyte. So the viscosity of the electrolyte changes during cycling a lot. And also, we can lose, because the capacity, because these polysulfides can be self-discharged directly on the anode side. So what we can do in order to solve this issue, there are several approaches. If you can check the literature, you will find a lot of publication with different possibilities. But let me summarize them in 2 different classes. One class can be the chemical anchoring of the materials, so it means that we are using some compounds within the cathode that are trapping the polysulfides and keeping them inside the cathode. So do not leaving, when they are formed, they still remain in the cathode and cannot flow through the cell. And on the other side are electrocatalytic materials that can accelerate the lithiation reactions and also the diffusion of lithium ion in the more viscous electrolyte. Here I'm really showing you a couple of results that we achieved in our group, and this is one of the results of the ALISE project that was performed by Usman Zubari, who was one of our PhD students and now professor in Pakistan University. He worked on titania. Titania is very cheap and easy to get. He prepared some materials hydrothermally with the titanium nanotubes that with the carbothermal reduction are transformed in spherical particles. These particles can really block the polysulfides that are forming. So after getting the wall material, sulfur was melted inside the structure. Let's remember that also the melting point of sulfur is quite low, so it's also quite easy to prepare in porous systems. So if you have a porous matrix, it's quite easy to make sulfur to move inside. And you can see very easily in this figure here that these are some solution containing polysulfides, and with using this kind of material, the color of the solution changes, becomes lighter because of the trapping of polysulfide. And you can see that you can also reach 1,000 cycle at 1C with this kind of material. That's quite good results. Another point of view is instead of putting elements inside the cathode is to put an interlayer. So you are producing the cathode and then you can spread and put another layer on the top. Maybe this is also taking into consideration also the manufacturing point of view. This can be also quite useful and simple way. Let me also add that when we are considering new technologies, we have on one side to consider sustainability, recyclability, and so on, but on the other side also the manufacturability. So we can also think to something completely new, completely disruptive. I think that in particular new generation will have very interesting and new ideas, but then we have to prepare them. And in my opinion, we cannot really consider that now we are building gigafactories and in a few years we are destroying everything, starting again from completely new technologies and so on. So if we can get something that we can combine and use at least partially what we already was invested, this is good. And sulfur can be a good solution because the production of the cathode can be not completely different. And so the idea here is the use of a layer that you can see here to put directly on the cathode. So you produce the cathode with maybe a roll-to-roll method that's commonly done for lithium ion, and then you can put this layer. This layer is a carbon nitride layer. This work was performed by Dr. Daniele Versace, which is a postdoc now in our group, and he received a prize just 2 days ago because of this work from the Italian Chemical Society for his work on this PhD thesis. And after some calculation, DFT calculation that were performed by Professor Leiva in Cordoba, Argentina, it was demonstrated that this kind of material can trap properly polysulfide. So this is a good way also to reduce number of experiments instead of trying and retrying and doing some work. It was defined by DFT which kind of doping was more useful to get the better trapping of polysulfide, but still having the possibility to get the reduction, easy reduction of that material after the, let me say, the chemical bonds produced together with these this layer. This is, in practice, the structure is similar to graphene, but you have a carbon and nitride there. You can see here that just in a simple graph that the standard material, the one without the interlayer, that is the black curve, performs much worse than the one with this. For future, we are considering that even the activities that are presented in Battery 2030 also, inventing the sustainable batteries for future, combining digitalization together with experimental activities and together the sensors that we can put now in our cells to measure, for example, at least the real voltage of the two electrodes and not the difference in voltage will really increase the rate to arrive to real production, so hope soon. I will conclude my presentation fast, just giving you another point of view. That is the one on potassium. This is not really my work, or better, is a work of our group by Professor Bella that is working on potassium. On sodium and also on potassium, and I'm here just to show you a different point of view. Potassium is also can be interesting for the future because it's highly abundant, as everybody knows. It's not so abundant as sodium, but still several times more than lithium, so good enough to get it. But its advantage is also related to the voltage. Its voltage is much closer to the one of lithium compared to sodium, so it can be a good idea for getting very high energy density. But better than this is that it can be intercalated in graphite, the difference than sodium that cannot be intercalated in graphite and forms bonds, and we have to use hard carbons in that case, or other materials, as for sure will be said better than me, and apologize for that in next talk. So here I'm just showing you that this can also be thought considering sustainability, as we were saying at the beginning. So here was the one work that was published this year by our group, in which we studied a separator produced with lignin, so that is coming from wastes of production in several companies, and with quite good ionic conductivity, around 10-3 at room temperature, and that also is not giving, let me say, disruptive specific capacities, but still can work for hundreds of cycles, and it's good starting point, let me say. So just very briefly to conclude, I want to say that for sure we need to think today to next future, so to something that will come after lithium ion, that will be solid state, that will be also other technologies, or they can be other technologies in parallel together with that, considering strongly sustainability, considering that we really have to know something more about the technologies, and the idea coming from smart functionalities that can be put, or sensors that can be put inside the cell, and all these operando techniques can be very, very useful for us, deep understanding of the technologies, and get quick advancement of all the system. And of course, all technologies should be developed, taking into consideration already now to manufacturing. So just I want to thank the European project that are funded today in our group and give me the opportunity to come here also, together with Battery 2030 also. And finally, the electrochemistry group and all of you for your kind attention. Thank you.
Thank you, Silvia. I'm sure this raises many questions among you and also online. Please start sending in your questions on the Q&A, you who are online. About a year ago, there was this announcement from the Chinese company Cattle that they would start production on sodium batteries. And that came a little bit like a wow in the community. And our European battery initiatives were quick trying to sort of make something of it. So we had actually, which is on our web, a seminar, an excellent seminar, where a scientific presentation was given by Monse Cabanas from CIC Energy Kune. It's really a lot of views on that one on YouTube. And then we collaborate with BID2022, who then, and it's in the same sort of film that you can view. We had a panel discussion between 2 SME companies from Europe and the CTO from Cattle. So, and moderated then by BID2022. And the 2 SMEs we immediately could identify. There's one in UK, but you know, okay, UK is, we want them to be with us. But the one was, earliest I think was Tiamat, coming as a result of the research in Amiens, Université du Jules Verne Picardie. I hope I can pronounce it correctly. Jean-Marie Tarascon, maybe more well known. But it came from that. And the second one was a company called Altris. I'm very now proud to present Professor Reza Younesi, who will give you the story, how it came from research to an SME company growing now, and why it's possible to grow it now after a number of years. I welcome you up on stage to give the story.
It's easier with this one, so you do hear me? Thank you very much, Christina, for the kind introduction. So I start with thanking the organizers for having me here to talk about sodium-ion batteries. So as it was said, my name is Reza Younesi, and I'm a lecturer at Uppsala University. So I'm going to talk a little bit about our research activities on fundamental understanding of batteries, especially sodium-ion batteries. But then I will shift to commercialization of sodium-ion batteries, as I have been involved as one of the co-founders of a company called Altris. So I'm sure some of you like fundamental science, so probably the rest will be boring, but some of you perhaps are more into commercialization. The fundamental part might be boring. So we will see if I manage to make everyone unhappy here today. So, but let's see.
Maybe you should keep the microphone a little bit closer to you.
Closer, okay.
Oh,
now it's
much better.
Okay.
Thank you.
So I was saying that if I manage to keep everyone unhappy today. But I start asking questions, actually, that might be better for me to see which part I should spend more time. Who is interested to fundamental understanding of batteries here? Okay. And who is interested to commercialization? So 50-50, that didn't help. Okay, let's start. So I'm not going to spend too much time on importance of sodium-ion batteries, because I'm sure you know a lot about that, and it was discussed a lot yesterday with very interesting presentation yesterday. But one thing we could learn from yesterday's presentation is that there is a high demand on being independent, especially in Europe, to being independent in energy production and energy storage, which has put a really high pressure on access to raw materials, especially raw materials used in lithium-ion batteries. So everyone is aware of the issue, which this basically means that we need to have other solution as a complementary solution to lithium-ion batteries. So it's not about replacing lithium-ion batteries with other technology. It's rather having number of solutions, because we need any possible solution actually in Europe. Any realistic solution actually is welcome to battery industry, as far as I understand, but it needs to be competitive and realistic. So of course people sometimes come with interesting idea, but when you go to the details, you can see that it's not actually competitive to lithium-ion batteries, and it's not maybe realistic. So being realistic and competitive technology is really the requirement to be in the same journey as lithium-ion batteries. So what we do at Uppsala University, we try to understand fundamentals of sodium-ion batteries, because one mistake that some people do is that they think it's very easy to move from lithium to sodium, because perhaps it's the same thing. You just change the cation from lithium to sodium, it's done. It's not like that. So we try to understand the differences in these two similar but different systems, And we use a number of advanced characterization methods in-house and also at synchrotron facilities, which highlights the importance of having access to synchrotron facilities in Europe to do actually advanced science. And with that, I will give examples of materials that we have developed at Uppsala University in the last few years, and this company called Altris, which was launched as a spin-off from Uppsala University. So this is a very simple picture of negative electrode in batteries with a layer on it called SEI. For those of you who don't know what SEI is a passive layer on the negative electrode. If it's lithium-ion batteries, then it's graphite. You have this passive layer, solid electrolyte interface, which makes the battery kinetically stable. Without going to too much details, this layer forms during the initial cycles in the factory when you make the battery, and it needs to be stable over long-term cycling. So what we have been trying to understand is to see what happens when you have this layer actually at the pause time with no electrochemistry. You form this layer and just wait for some time to see what happens to this layer. What you don't want is to see this layer is gone. And by gone, I mean it can be dissolved in the electrolyte, in the liquid electrolyte, or it can be decomposed to other species. So we try to understand this storage time. In a real application, you might see this as a capacity fading during the shelf lifetime, or you can say it's self-discharge, so the battery it will be discharged by itself with no external current or potential. So what we do is we cycle a battery, sodium-ion battery, as everyone does, but we make extended pause between cycles. So you can see that there is a long pause time after 5 cycles, and you can see that the time of this pause is changed. We started from 50 hours to lower pause time of 5 hours. And if you plot this pause time versus capacity loss, then you can see that there is actually a linear relation between the pause time, between the square root of pause time and the capacity loss. So this tells us that this loss is diffusion dependent. So when you have a square root of time, it's often diffusion. So from this, we try to have a better understanding by continuing experiment, doing the same type of test, but changing the volume of the electrolyte. And you can see on the right that there is, again, linear relation between this capacity loss and the volume of the electrolyte. The higher the volume of the electrolyte, the higher the capacity loss is. So this is also another indication that this is diffusion limited, and from this we concluded that actually SEI dissolution into the electrolyte is a problem for sodium-ion batteries. It is a problem for lithium-ion batteries, of course, any kind of batteries with this type of setup, but this has been addressed a lot in industry for lithium-ion batteries, but we need to have a better understanding of this for sodium-ion batteries. There's another interesting message from here that if you look at the figure on the right and the onset to the y-axis, you can see that actually the capacity loss is not zero when you move to volume of 0. This is interesting because then this tells us that this SEI dissolution is not the only issue that we have in sodium-ion batteries. So from there, we tried to continue a bit more to understand what's happening. If you look at the schematic picture in the bottom, on the right, you can see a schematic of this SEI dissolution. So you have the SEI, it can be dissolved into the liquid electrolyte. That's what you see on the right. And the electrode can be sodiated or dissodiated. In the middle, you can see that we also try to understand chemical growth of SEI. So that can happen with no external current or potential. So if there is any leakage through this SEI, the sodium ions can be leaked out from the SEI to react, and then the SEI thickness will grow. And on the left, we see this phenomenon called sodium trapping. If sodium is intercalated to the electrode, that sodium can further diffuse into the current collector and trap there. So it will be much more difficult to extract it. So you need to go very low current. So with those type of schematic figures and those type of cycling protocols that you see on top right, 3 different cycling protocols, we try to understand aging in sodium-ion batteries. And just to highlight the importance of this, if you look at the y-axis on the left, capacity loss, you can see that, perhaps you can see that, it is reported in microamp hour. So you can think about it, how small such a current and such a capacity loss is. This is almost 1/10 to 1/20 of the total capacity. So it's very, very small loss that is very difficult to quantify. And that's what we try to understand, to quantify such a small loss, because you may not see that actually in 50 cycles or 100 cycles. But when you go to commercial application, when your battery is supposed to work for 10 years, that's when such a small issue becomes big over 10 years. So that's what we try to understand. So this was the fundamental part, and of course it was very short snapshot of what we have been doing on the fundamental understanding, and it was example of one of the projects that we are doing. So with that, I continue with the next part, which is about a material called Prussian white. You see the chemical formulation top there? It's 2 sodium, 2 iron, and 6 cyanide. No nickel, no cobalt, no copper, nothing of those expensive elements. So this is not a new material. This is part of Prussian blue analogs, which has been around for many, many years. It has been used in painting and so on. But it's very interesting because if you manage to remove all the water out and have 2 sodium in the material, then you're going to get actually a very high capacity of 170 milliamp hour per gram. This is roughly in the range of LFP. And the potential is almost 3.1, again, in the range of LFP. This becomes very competitive to lithium-ion batteries then. The challenge is how to make this material. This is the biggest challenge. And if you look at literature, there are so many different results on this material. It's very confusing when you look at scientific literature. One of the best paper that you find actually on Prussian white is published by John Goodenough, which I'm sure everyone knows here. It's a very excellent paper, published a number of years ago, but the problem with that paper is that when you look at the synthesis, it's very difficult. It's high temperature, high pressure. It doesn't really make sense for commercial, large-scale production. So what we did at Uppsala University was that we came up with a method to make this high-quality Prussian white with much lower cost, which doesn't require any high temperature or any high pressure. So this material is now named under this commercial thread, phenol, which is coming from the elements used. And the people that you see there is Ronny Mogensen, my PhD student, or he was my PhD student before, finished a few years back, and William Brand, my colleague. So we launched this company almost 5 years ago, but things went very slow in the beginning, 2017, 2018, because it was difficult to convince people in EU and even in Sweden that this has some commercial interest. If you go back 3 or 4 years ago, it was really difficult to convince people. But we started anyhow, and things changed a lot since 2 years ago, especially when, as Christina said, when CATL came out and publicly said that we're going to produce sodium-ion batteries, and they announced actually the same material. Now everyone is following. So now there's a real competition on sodium-ion batteries. So what we did, we upscaled this material, the synthesis of this material, as you see, from very, very small scale to a little bit larger scale in the lab. Then we continued to even further, and somewhere around after 10 liter, we said that maybe we should leave the university. Maybe this is not proper size anymore for the university. And that's when we moved out. Where is Altris today? So what is Altris doing today is that this is publicly announced that there's a factory under construction in a city called Sandviken, which is almost 1 hour north from Uppsala. And there we're going to have production of this phenol material with a capacity of 1 gigawatt hour per year, which is roughly 2,000 tons per year. So that material will be available to any battery producer. We are happy to work with any battery producer in Europe especially. And we are also working on our cell pilot line production, which is in Uppsala, and we just started a few weeks back. And there we try to actually formulate sodium-ion batteries, how to make proper sodium-ion batteries by putting different elements. And that includes the electrolyte, the anode, the cathode, separator, casing, everything. So we try to push that forward, which we believe that by doing that, the cell producer in Europe and the US will be perhaps more keen to take the solution from here and make sodium-ion batteries. So a few months back, we had a round of investment when we got almost 10 million euro. This would be impossible, as I said 3 years back, but it is possible now. So we had 3 leading investors, including InnoEnergy, Northvolt, and Molindo. So there is clear interest. So this is happening. With this money, we're going to continue expansion, and we are hoping to have commercial production of sodium-ion batteries in near future. Another thing that we do in connection with Uppsala University and Altris is we have developed a non-flammable electrolyte for sodium-ion batteries, which is based on sodium bob. This is now patented by Altris. Sodium bob, for those of you in battery community, is not a novel thing. I mean, we have had lithium bob around. So the interesting thing is that if you look at literature, Stanley Whittingham showed how to synthesize sodium bob a few years back. But sodium bob is not soluble in carbonates and ethers. So no one paid any attention to this salt for a number of years. And then we found that actually you can dissolve this salt in phosphate-based non-flammable solvents, which is excellent because then it becomes non-flammable electrolyte with quite good conductivity of 5 millisiemens per centimeter at room temperature, which is not the best, but it's good enough for, especially for a stationary application, if you're going to push to C/2 or even C rates. And this is also next step for Altris to upscale production of such electrolyte. So with that, I can give an overview of what we are doing. At the university, we try to have fundamental understanding of materials in batteries, interfaces in batteries, to try to use advanced characterization tools to understand batteries better. And then with that, we try to move towards commercialization of sodium-ion batteries. So this is the last slide, the acknowledgement, but it's not just a simple acknowledgement. There are a few important messages, I would say, which I should deliver here, connected to this meeting that we have here. One is that all those good results and work, if you call it good, which I believe is good, is done by the students that you see here. It's not me, it's the students. So it's, you see Leon and Roni, they were my PhD students. So they did all the good work and now they are working in the company. So this highlights actually the very importance of the education in Europe, which of course, we have had a strong education in Europe. That's not a question. The question or the problem is to catch up with the speed of expansion of battery industry in Europe. You can continue educating good students in Europe, but if you look at the speed of industrialization of batteries, that is really difficult to catch up with. If you don't have a good students, if you don't educate good students, then there is no good industry. I don't have any solution for this, but I'm sure other people are more creative to come up with solutions. The other important thing which I would like to highlight here is you can see that we have this Ångström Advanced Battery Center. That's where we were actually initiated this company, and that's where we do all our works. But this center has been there way before me or any of these students arrived there, since almost 30 years ago. And people like Christina and Josh have spent huge amount of time and effort to have such a center. This is also a very important message that we need to have those type of well-functioning centers if you want to have innovation. Without having those type of centers where you can do really good science, it will be very difficult to have innovations. So it's a mixture of good education, fundamental understanding, and good access to equipment, synchrotrons, and so on. And the last one, of course, the funding. So, as I said a few years back, it would be difficult to convince these funding bodies to put money on sodium-ion batteries, but it's much easier today. So I can, of course, I could wish for more. I could claim that if we had more money from Swedish or European agencies, we could go faster and bigger, but this is maybe I'm biased, so I can claim that. But my point is that it's a very critical time for Europe. If you look at lithium-ion batteries, Asia has been the head. And then China took a very quick journey since 10, 15 years ago. They are now ahead. That is not the case with sodium-ion batteries yet. I think next few months to next few years is very, very crucial. If you don't work quick and strong, we will lose this competition. to Asian, for sure, there is no doubt. But there is still chance and possibility to catch up with this competition and be ahead with sodium-ion batteries and new chemistries. I'm not going to say sodium is the best of the best. No, we need to be competitive on new chemistries as a complementary to lithium-ion batteries. Thank you.
Thank you, Reza. We will now move into our third speaker, and I hope he's online, that we can see him. Yes, we can. Great to see you on the screen, Patrick. I don't know if you can see us.
Yes, we can. I can see you. Can you hear me?
Yes, we can even hear you, which is wonderful. So it's a good start of your presentation, and you are really far ahead working on some of the new emerging technologies, and especially combining both experimental and theoretical work, and with a view, very strong view, both on the full cell battery, but also on the electrolytes. We look very much forward to talk to you and listen to you. And again, write your questions in the Q&A. We will soon start the discussion. So welcome, Patrick, and take the screen, I guess I say to you. Please.
Thanks, Christina. And it's truly a pleasure to be presenting. I would like to thank the organizers for letting me come online and hold this presentation. I wish I would have been in Brussels, of course. But, well, you know, sometimes time is limited. I could have just started by saying concur with the rest of the people, but I would also like to say that I would probably go a little bit deeper and a little bit broader. I will cover lithium sulfur and sodium ion, but I will also try to cover some other post-lithium ion batteries. So next slide, please. So starting from the electrolytes point of view, it's very easy to think that the liquid electrolytes that we so very well known for lithium-ion batteries, in whatever shape they come and whatever additives we have a lithium salt and we have some solvents and a number of solvents perhaps, and a bunch of additives. But when we look at the post-lithium-ion batteries that I'm going to cover today, the sodium-ion batteries, the lithium-sulfur batteries, and the magnesium, calcium, and aluminum batteries, I'm going to bunch those all together. These are not the same. They are very different in return, but also the demands of the electrolyte development is very different for these. And I will bring you 4 perspectives to sort of get these on the same balance. So I will, those 4 perspectives is like, what is so special? And that goes both for the battery chemistries as such, and the electrolytes is special, of course. And what do we really know today? And what is the main challenge? Of course, that's where we need to work. And I'm really going to put this, as Reza put it here, is it fundamentals or more application side? I'm a professor of physics. I'm very much into the fundamentals, but you will see that there is a bearing on what happens on the application side. And then I think maybe it's a little bit preposterous, but really what should we do? What can we do? What should we do? And then my last sort of hobby horse is that it's very easy to hype both what the next generation batteries or post-lithium-ion batteries will provide. It's also very easy to hype time aspect. When will they be here? I think that everyone who's joining in Brussels and online here, you're quite aware of this. But there is a constant danger that we actually hype it ourselves. And we better be aware, because it will be a backlash if we don't. So next slide, please. So for sodium-ion batteries, as Reza really told you, they are here already. My personal story with that is that I both worked with Reza before he started with sodium-ion batteries, actually, and that was a pleasure, of course, with Christina as well. But also working with sodium batteries in the context of a CEA-run project, which later on has been much of the starting of the Tiamat. So if we just bring it down to very basics, so more like lecturing, so what's so special? Where we don't have graphite anodes, we can use 2 times aluminum current collectors, and that means that actually you can short circuit your battery when you're transporting it, and that is an advantage that is sometimes stressed but sometimes forgotten. I mean, this is really something that can be marketed more than it is. Something that happened during, I think it was this year, might have been previous year, was that there was a slide in production in a lithium-ion production site. And while I do agree with Reza that, I mean, you cannot just throw a sodium inside instead of a lithium there, but this actually tells you something about how close they can be and where they are in closeness of lithium-ion batteries as compared to the other technologies, which are quite different. We know a lot of things. We know what electrodes we can use. We know their pros and cons, of course. We have not established that there is only one, just as well as there is not only one lithium-ion battery. But for sure, we don't have sort of the standard electrolyte, and that comes back then to the LP30 thing, which you talked about earlier. That actually LP30, we don't have anything similar. And the main challenge is exactly what Reza started out with. Sorry for just referring to his talk, but it was actually really, it summarized the main points. I mean, one thing is really the larger solubility of sodium salts, and that in turn gives you the SEI instability, that it dissolves into the electrolyte. Another thing I would like to stress is that when you buy a sodium salt today, there are problems with both the purity and dryness. If you look in the literature, a lot of people use sodium perchlorate. That is nothing that would be ever used in production. I think that sort of tells you that those studies are of less interest, at least to me. But also, if you buy a sodium PF6, there might be a lot of sodium fluoride in it, and that is something that we actually have noticed ourselves, and that's a crucial thing to really keep an eye on. So what can and should we do? Well, more or less systematic evaluations, but then is the question: what is the anode that you're going to have around for those evaluations? That's not so obvious actually, because hard carbon, yes, but it's not only one. What kind of loadings should you have, etc. So there's many things like that. To locate sweet spots, even if you have like a standard setup of a liquid electrolyte, the role of electrolyte salt concentration, it absolutely don't need to be the same as for the lithium-ion battery chemistry because of the solubility issues. That is something that we looked quite a bit into to see how can, for instance, highly concentrated electrolyte work, and where you can have ligand exchange mechanisms that are quite different from lithium to sodium, and might also give you sort of hints why the sodium-ion batteries give so much better power performance rates. And then, of course, develop the electrolyte upscaling. We talked before about upscaling, but I also think the electrolyte upscaling is something where there is a lot of work to be done in the light of the dryness and purity issues, but also once you can finalize into an electrolyte concept. Next slide, please. So, as compared to sodium-ion batteries, lithium-sulfur batteries, which Sylvia covered, I mean, there is so much promise. The sulfur is a very cheap anode. Okay, it's not conductive to electrons. We have to have it in a carbon matrix. But the promise of a really high energy density at a low cost and also environmental impact is really fundamental. And having a lithium metal there, so it's a solid state sort of equivalent cell, but you can have a liquid electrolyte or a solid electrolyte, but you have the lithium metal electrode. One problematic, though, is that a lithium sulfur cell will always be a low voltage cell. For some applications, that is a crucial disadvantage. We're talking about approximately a 2-volt cell, as opposed to what people are doing for the high voltage cells, where you go more like 4.5 volts. So that's more than 2 times the lower voltage, and that might be a crucial disadvantage. What do we know? Well, we have so much carbon-sulfur composite designs. Some of it was shown by Sylvia. There is so much in the literature. We also have all the knowledge of the lithium metal anode. The old know-how really comes from the very origins before the lithium-ion battery, but we also have a lot of new know-how in the special context of a lithium sulfur cell, but also making use of all the development when it comes to lithium metal solid-state batteries. So the main challenge here is very different to the other chemistries, all the other chemistries I cover, because the fact that you're creating polysulfides from the sulfur host, and that means that your electrolyte composition will actually be a function of your state of charge. Of course, that is the case for other chemistries as well, but not at all to the same extent as for lithium sulfur cells. So to control and limit the polysulfide solubility by the electrolyte design, for instance, or by using catholites, which intrinsically has a lot of sulfur solubilized, that is really a key issue, a main challenge to be taken care of. And it's important to realize the polysulfide solubility is actually a function of the lithium salt solubility. That is something that we're doing a little bit of modeling on, where one can see that if you have, for instance, a fluorinated solvent, people say, yeah, but that limits the polysulfide solubility. Yes, but it does so by the fact that it doesn't solubilize the lithium cations. So that means if you link those two together, that means that the choice of solvent becomes rather tricky, because you want lithium salt present, of course, because that's going to be a charge carrier of interest. At the same time, it actually tells you that you're going to have some polysulfide solubility. So more complex electrolytes than perhaps has been studied so far. There are some interesting notions now where you have electrolytes that actually preferentially solvate the lithium cations and not polysulfides, and that's an interesting route to see some of that coming out this year. What I think we should do, that's very much basic studies. I mean, study really the initial solvation of the sulfur and creation of polysulfides at the very surface of the electrode. And that you would have to do using very high loaded electrodes and lean electrolyte conditions, because it's something about your solubility here. So you need to have both of those factors in the correct state. And then you have to apply an operando surface method. Those who see that kind of wish list, you see that, okay, so this is going to be complex. But people are getting there. We see that a lot of work at large-scale facilities, synchrotrons, neutron facilities, etc. People are aiming in this direction. I think that's totally the right way to go. It's really specific targeted experiments that are needed. And huge European efforts in this direction, absolutely the way to go. And I think we are getting there. Next slide, please. So this might sound very pessimistic, and this is actually where I myself prefer to work. So I don't know what that says about me. But all these chemistries where we're thinking now about multivalent batteries, we have metals, metal anodes, which all promise high energy density. That's the common demeanor, but they also have very different cell voltages, where magnesium is 1 volt above lithium approximately, calcium is very close to lithium, and aluminium is 1.5 volts above lithium. So that's quite different things. Dendrites, I mean, that's always the question when you're talking metal anodes. And well, not like lithium metal, but I think this image in the center, I think it's a paper from Oxford and Peter Bruce's work. You see that you can get that still. It's not like they never occur in these chemistries. You can absolutely see that. We also see that for both magnesium and aluminium, there seems to be a need always for having chloride present. The problem with that is that it's also corrosive to a lot of other cell parts, and that itself turns everything that you do into a problematic. Ourselves, we've been using tungsten current collectors just to have proof of concept, for instance, but of course that is not going to make it commercial. Another element seems able to protect by creating some kind of SCI. And this is something that I think is very interesting, that boron as an element seems to be very versatile, both in calcium and magnesium chemistry. It might be part of your anion, it might be part of as an additive, and probably something with the SCI. We're not really sure. Degradation products of the salt, etc., it might be there. So the main challenge comes back actually to these things with that when we're talking, for instance, that chlorine seems needed. You need a non-corrosive electrolyte, but it still needs to be able to activate your surface, and that seems to almost to be a contradiction in terms. Of course, it's not really that, but it seems to be. Solubility and kinetic limitations. We are talking multivalent chemistry here. Often the solubility is lower for a multivalent salt than for a normal alkali metal salt. Alkali earths are a little bit. And so far that has been very clear, because to get proper cycling, a lot of the experiments has been done at some elevated operating temperature. But perhaps we shouldn't let that hinder us. What says that we need to run all our batteries at room temperature? There are high temperature battery concepts, and maybe that's where our multivalent batteries concepts will take us. But that might also be a different niche of the market. Just coming very fast to what do we do, what can we do, and what should we do? Well, again, coming back to the chlorine-free magnesium and aluminium electrolyte chemistries. Very hard to do. We tried a lot, especially in my own research group. We had a lot of projects on that. It's super difficult. But I think we need to get there in some way, because otherwise the rest of the cell will really suffer a lot. When it comes to the boron chemistry, we really need to understand the relationship, what happens at the interface, but also understand the cation solvation as a whole in a lot of these battery chemistries. We don't really know so much about the cation solvation as we do, and not the mobility, etc. It's a little bit of limitation as well. Some of these nuclei you can run NMR on, some you cannot. Some give very broad signals, etc. So there are problematics also when it comes to experimental methods that are applicable. One hobby horse of mine when it comes to aluminium batteries is that aluminium batteries is one thing, aluminium ion batteries is something else. So if you're going to use, let's say, graphite, where you intercalate AlCl4, for instance, then you actually take an active role of the electrolyte to formate what actually is intercalated. And if you do that, you're never going to reach very high energy densities in practice. It might look nice, but you really have to calculate what does it mean to your cell design. So I think that the designing aluminium batteries where you really have no active role of the electrolyte, and what does that mean? That means actually the aluminium 3+ should be your active species. And of course, then those of you who know solvation chemistry are going to say that, oh, that sounds tough. And yes, I think it is tough, but I think it's also a necessary stage. And I think that's where we need to be. But then coming back to will we ever get there might be a very good, it's a challenge, as we researchers tend to say. And next slide, please. Which basically asks this to tell you that I'm done. And thank you for listening. And I hope this spurs some discussion of where we're going with all these post-lithium-ion battery chemistries.
Thank you very much. And thank you for pointing out so many of the challenges we have in front of us. And I will now open the floor for discussion. And I would like to go back to my first slide about this roadmap picture to ask our three. Please, Silvia and Reza, come up on the stage. I hope you stay, Patrick, because we have a question for you. And those of you who are online, write in your questions in the Q&A, please. We really would like that. So here it is. I will come back to that later, but I'm sure that in the audience here in the room, there must be some urgent questions to some of you. I see a lot of hands. Please say your name and where you're from and who you are directing the question to.
Hiya, my name is Rebecca Ford. I'm a PhD student from the University of Limerick. Really enjoyed all of your talks, so thank you so much. My question's directed towards Patrick, as I'm interested in aluminium batteries myself. You mentioned about chlorine-free electrolytes, which I've also looked into, and it is very difficult. Do you see any scope for using chlorine-free electrolytes in aluminium sulfur chemistry as well as aluminium ion?
Of course, a good question, and thanks for the interest in aluminium chemistry. We're not that many out there. We're getting more. I haven't worked with aluminium sulfur, I should say, but I think that the issue is more or less the same, although that you will need to transfer. You will need to transfer your aluminium 3+ to probably create an aluminium 2s3. At some point, and the more you have a too stable solvation shell, the more difficult it will be to formate and deformate that sulfide species, I guess. But I guess also what comes down to is like what are the possibilities? What can one do? I think that one has to think a little bit out of the box. Other aluminium salts, for sure. Other types of solvents. We are looking, for instance, into deep eutectic solvents as one possibility. Of course, that also comes with a little bit of problems with the viscosity. And when you have a sulfur battery, you might not want to heat it up too much. That's often a problematic when it comes to sulfur chemistry, right? So. I'm not sure if that answered the question, but it's a big problematic, of course, and you're not making it simpler by doing an aluminium sulfur battery. But the paper that came out just like 2 weeks ago from MIT, and that's a rather interesting paper where they actually also go up in temperature.
Thank you. There was another question close by here. If you send there, yeah.
Yes, hello, good afternoon from my side as well. My name is Hendrik Lebberding from FEV Europe, and my question is for Reza, I hope that's correct. And I would like to understand your insights on the producibility of the sodium-ion battery. You touched upon it just before, but I would just like to understand what's your view on how exact is the production process similar to conventional lithium-ion batteries, and will we actually be able to use the same production equipment for these types of batteries? Thanks.
Yes, that is actually one of the interesting points with sodium-ion batteries, that you can basically use the same line of production of lithium-ion batteries to produce sodium-ion batteries. And we think that's the reason that some of the big companies, either in Asia or in Europe, are now interested to sodium-ion batteries, because they can see that they can use more or less the same line using the same type of batteries.
Okay, there was another hand. Yeah?
Hello, my question is from Reza. I'm Mustafa Mohammadi, I'm a PhD student in Sorbonne University. Actually, I have a couple of questions, if you don't mind. You showed us that about the charging of sodium-ion batteries. My question was, what was your charging mode? It was pulse charging or current constant or something like that?
If you are referring to the study with the charge cycling combined with relaxation or pause time, that was constant current galvanostatic cycling.
And it was from 0 to 100 something?
So this was on hard carbon. So what we want to do is we would like to understand what happens to SCI on hard carbon. So we basically go down to almost 10 millivolt to sodium hard carbon and then make a pause to see what happens. We have done similar studies with higher surface area carbon black also, where we don't expect much intercalation, and whatever capacity we see is coming from SCI formation and ion adsorption.
Okay. And another question, you talked about the SCI is not stabilized. How you could manage to fabricate a cell with a stabilize? It's about your electrolyte, or is it another?
That's the tricky question, but to answer very briefly, this is the whole industry of lithium-ion batteries working for 40 years now to try to optimize liquid electrolyte of lithium-ion batteries with different additives, for example, or changing the salt or having co-salt and so on to make SCI more efficient. So the same thing is needed for sodium-ion batteries also. By using additives, co-salt or co-solvents, you try to optimize the SCI and make it more efficient.
Then I have a follow-up question.
Yes.
How would you accelerate that compared to all the time you spent on lithium ions to come where we are today? Can you speed that up so we are much quicker with sodium to take the competition? What would we do then? What would be needed? Don't say more money, because...
More money, but...
No.
but
be more precise.
Yes. I think one advantage that we have today compared to many years ago is that we have more advanced characterization tools, that we should use them properly. I'm talking about synchrotron facilities and also in-house facilities, that we can use them to have a better understanding, which means that we can be much faster today compared to 30 years ago on developing new chemistries, including sodium-ion batteries.
Have you any suggestions, Sylvia?
I have no particular suggestion, but yesterday we got, for example, some talk about robotization. For example, one of the issues for sure in new chemistry, but not only on that, is the optimization of the electrolytes. Sometimes you put very good additives for the anode that are making worse work in the cathode, so it's very difficult. And to try many different combinations is always more and more difficult. So robotics can really, Isidora showed us how they can, in few minutes or very short time, to get hundreds of combinations of electrolytes and select which can be better. For sure, this would speed up a lot the system compared to what we could do, let me say, 5 years ago. Can I say something like this?
Okay. Patrick, do you have anything to add to how we would accelerate? What tools we could use to accelerate this?
I know one thing that I hope that you wish that I say now, and I think therefore I will say it.
How predictable I am.
We have the Big Map project, which basically does all what we need for the lithium-ion battery, because we are then doing the really good modeling, we're doing the screening, we're doing the advanced surface chemistry and surface physics experiments, and we combine that into a common frame picture. Once one has done that for the lithium-ion battery, then the way forward is that then you have created a platform, a common language, and then you can transfer that to the sodium-ion battery problematic. So I would say that one does that, but you also combine it with some of your intrinsic know-how, because it's not, just the thing like Reza says about the sodium bomb. Without having the chemical intuition or the skill to predict that, it would not be a simple conclusion from having used LiBob before, because it was not used.
You're right. And that's hope for young PhD students. Your brains are needed in the future. Not everything can be taken by robots or algorithms.
Sure.
We need to have knowledge as well, human knowledge. That's good. Sure. We have here a question here from Venkat, please.
My question is also to Reza. My name is Venkat. I'm a PhD student from Helmholtz Institute, Ulm. I do sodium-ion battery cathode research. So I have two questions. Please excuse me if they are controversial. The first thing, so I've been noticing the sodium-ion battery companies from last 1 to 2 years. So I kind of noticed a scary trend. For example, Paradian started 2011 around, and they are still at the scale of very small scale, and maybe electric bikes. I think they are making electric bicycle. But if you must be knowing the company called Hina Battery from China. They just started like 2017 or 16, but they are doing already like crazy stuff, like more than 100,000 cells, like cylindrical and pouch. They have demonstrated electric vehicle. They have demonstrated 1 megawatt grid storage. So, and Altris also started at the same time, 2016-17. So they are, I think in my opinion, they're very much behind Hina, for example. So what is the thing that is fundamentally lacking in our approach compared to, for example, China? Is it the money that is lagging, or the way that we do is making us slow? So that's my first question, and after that I will ask the second one.
So how can they in China be so much quicker?
If you go back 2016, 2017, you couldn't find that much activities on lithium-ion batteries in Europe. Many of these initiations on gigafactories, including Northvolt, which is the leading in Europe, and then you have 3 in Norway, you have number in Germany, in France, and so on. Yeah. Everything has happened since 2017. So of course, that was the issue, that when you don't have that type of production, factories, infrastructure, then things will be difficult for smaller companies like Faradion, Tiamat, Altris, or any company to upscale. But things have changed. I think that's the beauty of today, that now there are gigafactories under construction in different European countries. Now it's time actually to be much faster. And as you say, there is huge effort in China, so we need to be faster in Europe.
Yeah.
Yeah, and another short question is the comparison between Altris and Northvolt. I think both also started at the same time. But Northvolt, I think they're majorly a cell developer, I would say. So they're already in $1 billion industry, and Altris is around few millions right now. So what is the main difference? Why they're growing so fast and Altris is still small? So
good question.
I wish Altris is so big. I am a huge fan of sodium-ion batteries. So
fine. Yeah. These are the two different companies with 2 different mentalities. If you look at what Northvolt has been doing, which is excellent, is to commercialize and commercially produce lithium-ion batteries. And that is just graphite, lithium, cobalt oxide, or NMC that everyone is producing.
Exactly.
So they are doing completely different things. They were going to produce a chemistry which other people have been producing for 20 years, but it still is such a risky business that they could not risk the chemistry. We discussed them actually in the first days that if they are interested to other chemistry, and the answer was no, back 2017, which is completely understandable because it's such a big business that they had to focus on one chemistry, and that was graphite versus LCO and NMC.
Yeah.
And they go fast because that's what is needed in Europe. Yeah. If you look at Altris or Tiamat or Faradion, this is a completely different story because they come with a new chemistry which no one has produced really before. So things will be slow. You need much more understanding, studies, development, and of course, we go slower.
It's difficult bet to convince investors. So that's why.
I would say that since I'm old, and I've seen many attempts to make lithium-ion battery companies in Europe, there were actually companies in production of lithium-ion batteries at the end of the 1990s in Denmark, one called Danionics, for instance. That is that Northvolt came at the right time, because it was then when the European Commission and the automotive companies realized we have to change, we have to go and do something. We can't live on the fossil fuels so much longer. We really need to do something. And we must ensure, because we have quite small volume per company, that we can have access to battery cells. If you then come and say, we are not an Asian company, we're a European company, and we can do that based on hydropower and renewable electricity, produce these batteries, you are at the right window. And then it's the lithium-ion batteries that the transport sector knows. Sodium is coming as Reza says later. But it's interesting how fast they can move in China. But I would like to move on to another question now. Okay, there was another question. Then I go for online after you, please.
Thank you. Bozor Kambay from BEPA, Battery European Partnership Association. And I have two questions, but if you have time, you can skip whichever.
Take
one from Reza. So we are providing the European Commission with the insights from the battery community for the Horizon Europe goals. And I was wondering if, what's your input to basically having less people like you in terms of being basically having attention of the funding agency. So in 3 years, there's someone else like you in 2017 saying we have this material, and how can we basically implement that in the research agenda?
I would say we need to have very open eyes on any interesting possible chemistry. We should not fight with each other on a specific chemistry. There is enough place for everyone. But I would go back to what Patrick also said in his first slide, don't hype. Because that is the problem, that there is like so much hype around in literature, in media, and people say, oh, we have solved all the problems. So how to have a balance of having open eyes while having critical thinking, that's a challenge. That's a challenge. There is no easy answer for that.
I mean, shall we just put a restriction, a commercial sort of restrictions on the research activities? So say, talk to me when you have tested it in a pouch cell. So, or it would be too restrictive. So we have to let the scientists just dream on, or there must be, I mean, CATL, there's a reason that takes the attention because they can make 280 amp hour cells. And people know if they go to sodium ion, at least they can make something. So,
I mean, on European level, perhaps Christina can answer better,
Sorry.
but on European level, of course, you need to have activities and money and research on all TRL levels. You need to have fundamental understanding. You can't just say that let's put all the money and focus on industrialization. You definitely need fundamental science, which I tried to say it in my last slide also. If we don't do fundamental science today, we will have nothing to come with as innovative, let's say 10 years later. You need that, but at the same time, you need industrialization. How to balance this? I have no idea. This is not my expertise. Other people in EU know better than me.
I can say Dynamics died because they didn't have a second generation of their chemistry once upon a time. Well, I have a question here from online. Could a move to solid electrolyte, especially sulfide-based, improve the situation about polysulfide shuttle mechanism? I first ask Silvia, then I move to our electrolyte expert, Patrick, on this question. So please, Silvia, do you have any take on this?
I said at the beginning of the talk that for sure all the improvements that are going to be done in the field of solid-state chemistry will be very useful to enable the use of lithium sulfur. And for sure, for a sulfide-based solid electrolyte will be useful to improve the safety of metallic lithium ion. To block polysulfides, the polysulfide shuttling is something that is related to the use of liquid electrolyte. There are different studies. Someone that tried to move directly from sulfur to lithium sulfide, which is possible, but there are a lot of kinetics problem, of course, so the reaction is much more difficult to be got. So still keeping some liquid electrolyte in the cathode will facilitate the shuttling of polysulfide to get easy the product of reaction, which is lithium sulfide. So for sure, protection of lithium is mandatory. Nevertheless, we have not the right safety, and this will be useful. Of course, if we have a good layer protecting lithium, we'll improve and we reduce the possibility to get the self-discharge of polysulfide directly on the anode.
Do you have any take, Patrick? See where you are.
Well, not so much to add to what Silvia said. I think she said it very clearly. But I think the one thing that I'm not a solid-state electrolyte proponent, really. I think it has a lot of problems, and you will probably need some kind of small amount of liquid electrolyte, because you will have this porous electrode that you would need to have a good contact with. And I'm not sure that is so easy between the sulfur solid state electrolytes and the carbon sulfur
Cathode.
Yeah.
It's blocked.
Oh, yeah. I think
carbon sulfur cathode.
I'm sorry, yes.
You froze on our screen. Sorry about that. I would like now to end with my slide on this, which is, I think, possible to put up. I see it on the screen in front of here. And ask each of you, if you look at this slide now, you can turn around and say, is any one of these wrong, that you should move out of the picture, and have we forgot something? I think allow you a little bit of thinking on this. And I ask all of you, do you think that we will see advanced lithium metal battery, solid state, already 2025? How many of you believe this? And the ones that are polymer-based will say yes, like Blue Solutions. Do you think you will see it with ceramic electrolytes? No. And this is the tricky thing when you're trying to put something on this. Yes. I see that Sylvia has been thinking for a while. Have you anything you would like to move around on this picture?
I really have not the magic wand, so it's very difficult to say who will arrive and when. For sure, my thinking is that really we have to try and to get development of everything. Then my idea is that we will not have the only, let me say, chemistry that will win. We will get a big diversification of possible chemistry. We need a lot of batteries in the future if we really move faster to electric transition. Some of them, for example, stationary sodium will be for sure something very interesting because of sustainability and so on. I'm not very sure for automotive application, for example, where maybe other chemistry will win, but we have many possible solutions. We need to electrify from bikes to a big truck, so everything will have a different kind of storage system, maybe not only batteries. I do not see aircraft to fly with batteries, frankly speaking, by my opinion. But the smallest it is, the better is a battery, the bigger is it, the better it will be fuels, different kind of fuels. And so really here, everything should be kept, and it's very difficult to say when, I think.
Patrick, the obvious question for you is, of course, do you believe that the multivalent systems, calcium, aluminium, magnesium, and zinc, would come 2030? Or should one push one to even further?
I think that one needs to push it even further. But at the same time, I would love to just take a few minutes to go back to something that we talked on before, about time issues, and I think there was an excellent question pushed by what happens in China, etc. And I remember, Christina, you were with me in Tianjin 2008. That's just 14 years ago. Only 14 years ago for some people in the audience. I know it's a long time ago. But the discussion taking place then was only about how should we as battery manufacturers survive. No one wants our batteries, there is no market. And I mean, come on, what does it look like today? And that was just for one single battery chemistry, basically, because it was 95% lithium-ion batteries being talked about. So things change rapidly. I think that if we look at this now 14 years, then with 2036, I think maybe we're then having a little bit of diversity. Maybe we're having 2, maybe 3 really big commercial batteries. Then we might have some smaller niches. But the thing is that we're driving electrification so fast that there is, as Sylvia said, such a big need for a lot of different chemistries, because otherwise we will not have the resources. we will deplete our resources and cost will go up. We see the lithium price going up 600% right now. I mean, that is not sustainable both ways, both price-wise and resources-wise. So it comes back to sustainability again. Everything comes back to sustainability.
Thank you, Patrick. And the last word to Reza then, before we end.
I second with what Patrick and Sylvia said. I also think there will be diversity of chemistries and battery types in future, and that's what we need. But I would like to highlight what I had in my slides also, that any new chemistry, any new battery needs to be competitive in terms of cost and energy density with lithium-ion batteries. Otherwise, it will be difficult to have it in the market.
Thank you. Thank you, all three of you, very much. And I'd like to give some homework to the young people that they expect to exist 14 years from now on. Please come up with the idea that is on this screen, in this roadmap, what the seasonal storage battery would be, because I don't think it's defined in that picture. I think we just you need to define it, then you have a super future. I found a paper on myself where it said that Uppsala University has made the battery that lasts for 1,000 years. I'm very glad that paper is hidden, because that could lead to a hype, and it hasn't done that. I'm very happy for that. So go home and be creative, and don't make any hypes, but make realistic things that really gives us a future, sustainable future. Thank you so much for all your contributions.